Yeah, if you want, you can share now. Yeah.
So Shobhan, did you already convey the change to the
Yes, yes,
participant?
I did. Yeah, I did yesterday.
Okay, nice.
I think usually by 5 we would have the full set of participants. Yeah.
6-5, you mean? Yeah,
Yeah,
sure.
6-5. Sorry, 6-5. Yeah.
So for Friday, Purvi, I mean, so did you ask that already? So
No, I
Shobhan,
did. I did not ask. I did not ask her yet. Yeah.
Purvi, are you there? So for Friday, I mean, do you want to take 2 lectures on Friday or 1 on Saturday? What did you prefer?
I think I slightly prefer doing both on Friday, but if it suits you better, I can do 1 on Friday.
No. Either is okay, actually, not a problem. So just wanted to know, so as to announce to the participants, that's all.
Okay.
Yeah, so we'll have then 1 today, 1 tomorrow, and 2 on Friday, right?
Yes.
Okay.
Okay, I think it's time. Should we start or wait for maybe just 2 more minutes? Yeah, it's 6 o'clock. Yeah. Okay.
Yeah, I just logged in, but I will leave in 5 minutes. So Shobhan,
that's fine. Yeah, no problem. Yeah, sure.
So Shobhan, you'll be there throughout.
I'll be there.
It may not be, if somebody is raising their hand or something, I might not be able to see it the way it works. So you may have to interrupt me.
Yeah, sure. And usually we have allowed all the participants to unmute and ask questions. Yeah. So even if someone puts something in the chat box or raise hand, I will let you know. Yeah.
Thanks a lot.
Yeah. Okay, I think we will begin. So good evening, everyone. So today we have our speaker, Professor Purvi Gupta from IISc Bangalore. She has done her PhD from University of Michigan and postdoctoral studies from University of Western Ontario and Rutgers University. Her primary area of research interest is complex several variables. She has published several papers in reputed journals. I thank Purvi for accepting the invitation and welcome you to the workshop. Yeah.
All right. So thank you for the introduction, Sushobhan, and good evening, everybody. So first of all, I'd like to say that at any point of time, if you have any questions or have any comments, please feel free to unmute yourself and ask. I'll also pause once in a while to see if there are any questions. And also, so over the course of 4 lectures, my goal is to review the fundamental theorems of vector calculus for you. And as you may already be aware that these results that we are going to do, they are actually all special cases of one single theorem. But whenever we encounter multivariable calculus for the first time, we always treat these results as individual results in their own right. So there are certain advantages to that. First of all, that reflects the historical development of the subject. But also, I think we understand their significance better if we view these special cases individually. So why are these results important? Well, one reason is that they actually help simplify a lot of computations, which already is a big plus point. But more importantly, they help us understand several physical phenomena and despite being results about integration, or in fact, because they are results about integration, they actually help us derive differential equations to model physical phenomena. So I am not a physicist. I will sort of hesitate from going on about physics too much in these 4 lectures. So I'll try to focus on the mathematics. But just to give everything some context, the 4 lectures some context, I thought we could start with a story in physics, and then sort of take off from there. So what are going to be the key objects that we will encounter? So we will always have a vector field, either in 2-dimensional real space or in 3-dimensional real space. So either in R2 or R3. And sort of vaguely speaking, what is a vector field? So in R2, it is an assignment at each point of a 2-dimensional vector, at least in our setting. And I mean, doesn't have to be a 2-dimensional vector, but in our setting, it will be a 2-dimensional vector. And in R3, it will be an assignment at each point of a 3-dimensional vector, which of course the vector can change from point to point. All right, now what are the other objects in play? So these can be curves or they can be surfaces. And then if you are also looking at 3 space, they can be sort of solid objects which have some sort of surface as a boundary. And so what is the story that I want to start with? So what is my vector field in this situation? So imagine that you have some sort of fluid that is flowing either in 2 space or in 3 space. And the system is such that the velocity of any particle in that fluid does not depend on time, but it depends on where you are. So the location of the particle. Okay, and so that velocity I am going to represent, so that velocity is going to be my vector field. So it has both direction and magnitude. And then what are these curves and surfaces doing in there? So these are some sort of objects that are sitting inside this flow. So you could have a wire sitting inside the flow, or you could have some sort of thin sheet made out of some floppy material that is sitting inside 3 space. And that sheet has a boundary along it. So that boundary is my curve C. Or you could have some sort of solid region that is surrounded by a membrane. So for example, you have a ball and the surface of the ball is some sort of membrane that allows the fluid to go through. Okay, so of course we are making a lot of simplifying assumptions over here. But what are some things that we can try to compute? And in fact, there are 2 integrals that we will encounter a lot. So what do these compute? So the first one is to do with curves, and this is what one would call the circulation of the flow along the curve. So rather than give you a very precise meaning, what this really means is that you kind of want to know that what is the tendency of this fluid to flow in the direction of the curve. So if we take this motivation in mind, so here I have some notation for it. It may not make sense right now because we haven't defined any of these terms. But just to take motivation, I have 2 pictures over here. In the first picture, it's clear that the flow is heavily in the direction of the curve. And in the second picture, the flow is sort of perpendicular to the curve. So we expect the circulation to be quite high in the first picture and quite low in the second picture. Okay, and so then eventually this will turn out to be the case. So of course, one can do this for curves in 2 space or in 3 space. And the idea is how is it related to what is happening inside the curve? So there is some region that the curve bounds. This information is some sort of macroscopic information. And how does it relate to sort of microscopic information about the flow? And the second thing that we may be interested in is sort of like a dual object. So you have this flow. So think of it as some sort of liquid. And you might want to know that at any given point of time, what is sort of the outflux or the influx of this flow? So what is kind of the mass per unit time that is flowing out either inside or outside the system? So this eventually will be denoted by this notation over here. And again, you can sort of imagine situations where you expect the outflux to be very high. So if all the arrows are pointing out perpendicular direction, then that would be a high outflux. And then you sort of expect the opposite sign if all the arrows are sort of pointing inward. Okay, so this is just to give you some motivation of where these integrals are coming from. And in fact, sometimes when you solve problems involving these theorems, you are asked to compute a flux integral or what is the circulation integral. And these are not just random terms. They are basically coming from this kind of a discussion. Okay, so I'll sort of get started with, so we'll start with integration on curves, and I'll just start with that, but maybe let me just briefly pause and see if there are any questions or comments, anything at this stage. Okay, so sort of I'll kind of trust you to interrupt me and ask if there's anything, but let's get going. So we'll start with defining what a curve is, because that's going to be one of our central objects. So, so we have to be a little careful over here, and I'll sort of point out. All right, so maybe let me check. So as I write, is it sort of appearing on the screen?
Yes.
Okay, great, thanks. All right, so definition one, what is a curve? So a curve in Rn, and for the moment, I'll just work in all dimensions. It doesn't really matter at this stage, is a continuous function gamma from some closed interval in the real line into Rn. And let me just, for the sake of completeness, write down where AB is a closed interval. It's a closed bounded interval. So at least for the purpose of this discussion, that's what we are going to work with. Now, I'm going to add several adjectives to this curve. So if we say that, or let me write it this way, if gamma is continuously differentiable. So remember, gamma for us is a function, okay? And I'll say a little bit more about that distinction. So if gamma is continuously differentiable, so hopefully you've already discussed vector valued functions and what it means for differentiability and continuity of vector valued functions. So I'm basically asking that each component have that level of regularity. So if gamma is continuously differentiable on AB, then we say that gamma is a C1 curve. So I'll use this notation C1, and we call gamma prime of P. So now gamma prime of P is well defined, and at each T, this is a vector in Rn. And we call this as the tangent vector of gamma at T for any T in AB. Okay, so I'll sort of come back to the way we have defined tangent vector and C1 curve. Now, a lot of times, this is not available to us. So this something this nice is not available to us. But what we allow is that we allow that there can be some problem, some finite number of problems in our curve. So how do I specify that? Now, suppose if there exists a partition, and what am I taking a partition of? So my partition is basically a partition of this interval AB. So I have this interval AB on which my curve is defined, and I'm just breaking it up into finitely many pieces. And so what I'm going to do is my first piece, my first point is just the left endpoint, and then I have certain number of points. So let's say n plus 1 points, and the last point is the rightmost interval. So I have this. Okay. So suppose if there exists a partition P such that when I restrict this function to each of these sub-intervals, and these individual restrictions are continuously differentiable. So here J, it goes from 0 to, I guess, n minus 1. Then we say that gamma is a piecewise C1 curve. And often piecewise, I will just write as PW, C1 curve in Rn. Okay, so what's happening over here, and we'll do examples. The point is that this is a slight weakening of the previous definition because there are certain points where, by the way, something I should make clear over here is that when I say the restriction to each subinterval is continuously differentiable, that means at each left endpoint and right endpoint, I do have a well-defined gamma prime. But it's just that when I jump from one interval to another, the point where those two intervals match, the gamma primes coming from the two directions, they may not match. Okay, so that is the key difference over here. Okay, so we'll come back to this in a moment. So let me make another definition over here. So there are lots of additional conditions we need to add. So suppose we have this. So suppose we have a C1 curve. Suppose gamma is continuously differentiable. And so this is kind of an additional condition that I'm asking for. I assume that gamma prime of t is not the zero vector for all t in the domain of this function. Then we say that gamma is a regular C1 curve. Okay, and we'll talk a little bit more about the distinction between B and D. And then, sorry, so my screen seems to be a little stuck. Okay, and then a couple of more things which are less to do with the regularity of the curve. We say that gamma is simple if the image of gamma does not intersect itself. Okay, what does that really mean? i.e., if I restrict gamma to the open interval, then it is injective, it's 1-to-1 as a function on the open interval. And when I look at the endpoints, so the endpoints might coincide. So it could happen that gamma of A is equal to gamma of B. We don't have a problem with that, but they should not go and hit any other point in the curve. So if I look at the image of the open interval AB, then the two endpoints should not land anywhere over there. Okay, so I'm not allowing, if I look at the image, I'm not allowing something where this is what gamma of A looks like, and this is what gamma of B is. So this is not allowed, but I could have that gamma of A is equal to gamma of B. This is fine, this is allowed. Okay, I will call whatever function I get over here, I will call that a simple curve. And finally, if gamma A is equal to gamma B, we say that gamma is a closed curve. Okay, so let me just make a few remarks over here before I pause for clarification, and then we'll do some examples. So some remarks. So often the terms curve, simple, and closed can be used interchangeably for gamma and the image of gamma. So when I say the term curve, I think most of us imagine, an actual curve in the space. We don't actually imagine a function. We think of gamma, the function of, so the correct term is parametrization. I mean, if it has to satisfy certain conditions, but we don't really think of the function that defines the curve. We actually think of the image. But because we want to do analysis, we have to worry about this gamma. Now, in these definitions that I have made over here, definition A, E, and F, there is no source of confusion if I call the image a curve or if I call the function a curve. Similarly, when I say a simple curve, then we have already described what it means, that it will not self-intersect. And then if I say it's a closed curve, then we know that it should be a loop. Okay, and so second important point is, now this is sort of a deep theorem.
Ma'am, in the definition E,
Uh-huh.
is this gamma A and gamma B should belong to or does not belong to?
Does not belong to. Thank you. That is extremely important. Thank you very much. Yeah, yeah. Right. So, right. So we do not want the endpoints to come and meet the inside of the curve. Thank you. Actually, yeah, maybe this is not a bad point to pause and see if there are other clarifications about these definitions. Since we are going to, I'm sorry, because of the screen, I have to keep scrolling, but maybe let me give you half a minute to stare at these definitions. Okay. So let me make the second remark, which is actually a deep result, but we are sort of going to take it for granted because a lot of times the objects that we are working with, they're so nice that this seems almost an obvious thing to state. But this is known as the Jordan curve theorem. And what this says is that every simple closed curve in R2 divides the space, the 2 space, into 2, and I'll use these words, it doesn't matter, you kind of have an understanding of what this is, into 2 connected regions, which I will say as inside and outside. And as I said, that for a lot of things that I can even draw on this slide, it's kind of obvious what I'm referring to. I have a simple closed curve over here, and I obviously want to refer to this region as the inside and then this region as the outside. But if you kind of make this very, very, very complicated, then it's possible that it's not easy to distinguish the inside from the outside, in which case one actually has to prove this, that it itself requires some effort. But for us, it matters. And why it matters is because often, as I said, we will be interested in doing something along the curve, and we will transfer that information to the inside of the curve. So it's important to have an understanding of what inside means. Okay. So let me, before I make some more definitions, let's do some examples of things that you may encounter when solving problems over here. So the first one, I think we almost always have to start with this example. And anytime somebody gives you this expression, you should be able to recognize what this is. So gamma of t is cos t comma sin t. So I'll in my examples, I'll always look at curves in 2 dimensions just for the moment. And so what shape does this actually trace out?
Circle.
So this is going to be a circle. In fact, we know that it's a circle centered at the origin and of radius 1. And so now all our definitions, all the adjectives apply to it. So this is a simple closed regular C1 curve. And remember, I'm saying this about gamma. Okay, so gamma is a simple closed regular C1 curve. Okay, good. So let's move on to the next one. So I'm going to do a slight modification and we'll come back to this example because I have a question for all of you. Okay, so the second example I want to give is I take this same object, but I kind of do this seemingly trivial thing that I raise both the components to a power 3, and we can take the same domain, 0 to 2 pi. By the way, something that I haven't mentioned this word yet, but in the previous example, there is a direction of movement. So if you think of this gamma as some sort of tracing a particle, then as t goes from 0 to 2 pi, we are traversing the circle in a counterclockwise direction. Okay, that is sort of implicitly present in this definition. Okay, now let me come to the second shape. So does anybody know what this shape looks like?
Asteroid.
Correct. So yes, it is an asteroid. And let's draw this. What does this look like? Very good. So these are kind of important shapes. So this is what it looks like. So excuse my drawing, but I think I've sort of captured the spirit of this. So you're right that this is an asteroid. And I guess this point is 1, 0, and so on, 0, 1, and so on. And once again, here also there is a direction of motion. Okay, now you can check by differentiating that actually gamma prime is going to vanish at these 4 corners. However, the point is that this is still, so this is a simple closed C1 curve. Okay, gamma is a simple closed C1 curve. So the reason why I wanted to do this example is the way we use the term C1 curve. Okay, remember that is for the function gamma. But the reason why I wanted to do this example is the image of this curve has corners. Correct? So just because I have a continuously differentiable function that traces out this curve, that doesn't prevent the curve from having corners. Now, I have a couple of questions at this stage before we maybe do our final example. So a couple of questions at this stage are, so in example 1, we had a regular C1 curve. Can we have a irregular function? So can we have an irregular gamma whose image is still the circle? So can you give me some other, let's say sigma, so that when I look at the image, then it's still a circle. However, it is not a regular C1 curve. And I don't want a formula, I just want the idea behind it. How can I do that? Remember that what does an irregular parameterization mean? So I still want it to be C1. So let me still call it C1. I want it to be continuously differentiable, but there could be points where gamma prime vanishes. So what would be the idea? What makes gamma prime vanish? Geometrically, maybe.
Some peaks or some like the lowest points.
Okay, so your idea is that maybe it's some sort of maxima or minima is
Yeah, sort of, yes. Or
okay.
the tangent is parallel to kind of.
Okay, so one thing I should, okay, so you're thinking sort of correct, but remember that gamma prime t for us will be a pair, so it will be a vector. Okay, so when I say that this vanishes, I'm not just saying that this vector has slope 0. I'm saying that this vector is the 0 vector. So what you are saying, the parallel one, so if I take this classical parametrization of my curve, it is true that at this point, my tangent vector will be parallel to the x-axis. But that doesn't mean that gamma prime is vanishing here, right? Gamma prime is not vanishing here for this gamma.
Yes, right.
Correct. But so now with this point, keeping this in mind, I'm now asking what would make gamma prime of t become the 0 vector? Okay, so I'm not currently going to answer this. We can always come back to this. I want you to continue thinking about this. I have a second question for this example 2. Now I want to same curve. Now I want to ask, is there a regular C1 parametrization for this curve? So you can give me your instinctive answer, but then after you give me your instinctive answer, I also want you to tell me possibly why could you justify that, or how would you think of justifying it? So do you think this curve could have a regular C1 parametrization? So let me point out here that the one that I have given you is not. because at these 4 corners, if you compute the derivative, you will get vanishing. Any ideas? Or at least just a yes or a no? No. Okay. So I've at least got one response. So any people want to support that or not support that? What is your gut instinct whether it's going to have a regular parametrization or not? Okay, so I'm going to let you think about these two, and depending on the time, we can always revisit, or we can, I can talk to no. Okay, so another no.
Can we use a chain rule in this, ma'am?
Okay,
Because
so what's your idea? Let's take a look.
Another reparameterization would be said composite map of that.
Okay, so you want to say that, so you are trying to say that if there is a gamma tilde satisfying this, then gamma tilde should technically be gamma of something else.
Yes, ma'am.
Okay. So here we have to be a little careful in that this may not always be true. Okay, so they can be, so you're right, there is a theorem like this and we will state it, but not all parameterized. So it's not like if you give me any 2 parameterizations, then they can be related like this. So you're right that we will be able to, so now if I apply chain rule, I will get gamma prime at phi dot phi prime. And here this dot is really an inner product because these are vectors. So we'll come back to this later. And as soon as gamma prime vanishes, gamma tilde prime has to vanish. But my point is that not every reparametrization has to have this relationship with gamma. Okay. And so what I would encourage, and the justification for this will come from if you answer the first question. So the first question, I will give you the answer, but not the justification. So you can parameterize the circle to have an irregular parametrization. That means you can simultaneously have irregular and regular parameterizations of the same curve. So that means the chain rule argument will not always work. But there is a different reason why the answer to this is no. And if in your mind you're thinking that the reason are these corners, you are correct, but you need to find a way to mathematically justify this. Okay, so this chain rule idea was good, but it doesn't cover every case. There could be some sneaky parameterization, some bad one that somehow makes all of this work. So what we'll do is I do want to be able to talk about enough things. So maybe I can always ask the TAs to revisit this question, and this can be discussed. If there are any quick comments about it at this stage, we can do that. Otherwise, I'll move on. So let me write down this idea here for you to think a little bit about, but unfortunately that doesn't work. Okay, and then let me give a third example, and these are all things that should encourage you to think about these things a little bit more, because we are actually all very good at integrating along curves, but I think we don't spend enough time actually thinking about these curves. So let's do a third example. Again, the shape is kind of, I'll actually first draw the image of the curve, and then I will write down the parameterization. So again, my drawing is not ideal, but hopefully it serves the purpose. So this is the point 1, 0. This is the point -1, 0, and so on. And I want to give a parameterization that essentially picks up this direction of motion. And you can sit and try to do this parameterization. It takes a little bit of time. And if you go home and try to do this on your own, there's a reason why I'm asking you to do this on your own as well, because you want to note that sometimes trying to parameterize these curves takes a lot of effort. Okay, so there's a reason why I'm saying this. We'll come to that later. So of course, I may have introduced some sign errors. So you also want to check that what I'm giving you is completely correct. But minus 2t plus 5, t goes from 2 to 3, and then finally my last piece is 2t minus 7 comma minus 1, where t is in 3 comma 4. And so what I am giving you, so my gamma over here is going from the interval 0, 4 into R2. It's clear that, I mean, I started with a square, that was my intention. And if you look at these various pieces and you compute the derivative, so on each piece you will have a differentiability, but there will be some problem when you skip from one piece to another. So gamma here is a piecewise C1 curve, C1 simple closed curve. So the other adjectives are fine. Okay. And I have the same question over here. So here we had to go to a piecewise parametrization. Does the square, this square, admit a C1 parametrization? And you can choose your interval. So I'm not saying on this interval, you can choose the interval of your choice. And the second question is, does this square admit a regular C1 parameterization? Okay, so these are all very similar questions, and I encourage you to think about this, but let us move ahead and let us come to this question of orientation that we were discussing some time ago, or at least I vaguely alluded to. Okay, so definition 2. So given, and I also should keep track of time. Okay, fine. So given a C1 curve, gamma A into Rn, we say that, so if I have another object sigma, which is another function sigma CD to Rn, we say that sigma is A, an orientation preserving reparametrization if there exists an injective C1 smooth phi that goes from the first interval to the second interval. So it is injective and surjective with, and this is the key point, I'm asking for the derivative of this function to be positive everywhere. So this is what preserves the direction of the motion. So first of all, if I'm not allowing it to vanish. Let me just see. I see something in the chat. Okay, fine, it's fine. So phi prime t is positive. So this sort of says that whatever direction of motion gamma has, sigma will still have the same direction of motion, and such that, so first of all, this condition is satisfied, and the second condition is what we just saw, that gamma is nothing but sigma composed with phi. So remember, phi goes from AB to CD, then we compose it with sigma. That gives us our original parameterization. So if I have something like this, then I call it orientation preserving. And in the interest of time, what I'll do is, you can almost guess what orientation reversing will be. Parameterization, so everything else is the same, but I want phi prime of t to be negative for all t in AB. So this reverses the direction of the orientation. And by the chain rule argument that was being suggested by the audience earlier, you will notice that if sigma is irregular, then gamma has to be irregular, because phi itself always has positive derivative, or sorry, non-vanishing derivative. And if sigma is regular, then gamma has to be regular. So you cannot go from any parameterization to any parameterization via this method. You will always, within regular parameterizations, you can possibly go from one to another. And within irregular ones, you can possibly go from one to another. But there is a relationship that this is forcing. Okay. Any questions at this stage before we finally define integration along curves?
Ma'am, are regular curves dense?
So dense in what?
Dense in metric as a R-square Euclidean metric. The set
So
of regular curves.
So I need okay. So I need to understand your question maybe better. So yeah. So what is your space in which you are asking for density?
R-square.
Right. So, but then the set of curves is not a subset of that, no? So when we talk about density, then we have to think of set of curves as a subset of something.
These curves are, I think, subsets of R-square, not. No, they are the power set. They are in the power set of
So
R.
if you want to ask about whether they are dense in the space of subsets of R2, then you have to give me some topology on this to talk about density. But there could be a question I think you may be asking over here. This is a modification. You could be looking among all curves and then saying that you want to approximate this curve by a regular curve.
Yes, ma'am.
I think that's what you're thinking. You're looking at set of all continuous curves. So our curves are continuous by nature. And then you have some notion of distance between them. Let's say some notion of distance. And so depending on your notion of distance, yes, I mean, so you have to, yeah, yes and no, I'll say. But this is the correct problem. This is the correct formulation of your problem, I believe. So, yeah, I guess this is the correct formulation of your problem. Okay, but you're assuming regular as well.
Yes, ma'am.
Yeah. Then no, you can have very, very bad continuous curves, like with lots and lots of corners, and then you might have some trouble over there. But again, I'm saying that this really depends on the way you're measuring distance between two curves. Okay, so there are some.
Okay, ma'am. Okay, understood. Actually, I wanted to approach this problem of reparameterization through this approximation.
That argument. Okay, but be careful over there that density will not tell you something about a specific curve. So what will happen is if you take a really bad curve, you could be able to say that there are regular curves close to it, but this problem will not tell you whether that curve itself has a good reparametrization or not, because density only gives you closer and closer. And then of course you have to try to prove something like closedness, and that's going to be hard. Because in general, the space of regular curves is not going to be closed, you know, whatever metric you want to try.
Got it.
But it's a good strategy, because what happens is that it may be that you're just in a situation where your curve just does not have a regular parametrization, but for the purpose of your problem, an approximation works. So you could approximate it by a regular curve, and then you could do something with, I mean, that does work in a lot of situations. So at the end of the day, it depends on the application, but yeah, it's a good strategy actually. Good, okay. So so I'm glad that people are still thinking about those questions. That is really the purpose, because you probably have seen a lot of this stuff. So let me, so that we do make some progress, let me finally define what integration along curves means. So there are two things over here, okay? And the distinction is super important at this stage. We will always have, let's see, Rn. Okay, I'm still in Rn. Let gamma be a C1 curve. So at the least, I will assume C1. And I will also look at its image, which is some subset of Rn. And you can take R2 or R3 if you wish. So the first kind of integration is for for functions. Okay, so what are sometimes also known as scalar fields. So okay, and let me do the following. Let U be a region containing this curve C in Rn. Let phi from U to R. So it is a scalar function. So it's a continuous be a continuous function. Okay. Then the integral of phi along, let me say it this way. The integral of phi with respect to arc length on gamma So this is my main definition is, so the first piece is just notation. So I'll denote it by phi ds. So this is purely notation at this moment. And I'll write C over here, but I can also write gamma. And the way I define it is I will do it via this map gamma. So I'll define it as phi of gamma t times the norm of gamma prime t. So this is the Euclidean norm. Remember, this is a vector dt. So I have completely reduced it to a one variable integral. And this is when you have some sort of a function defined on your curve. This is my first definition. But more often than not, we will be interested in integrating vectors along a curve. So how does one go about doing that? So now let capital F from U to Rn be a continuous vector field. So this is a vector field on U. Now, this is a key definition, the integral of F along gamma. So how is this defined? Is, again, the left-hand side is pure notation at this stage. I'm deliberately putting a dot here, C. And this definition is, again, via gamma. I have F of gamma t. This is a vector. I take its dot product with gamma prime t. After taking a dot product, this just becomes a real number. So I can integrate this dt. Where, because I have not explicitly written this out anywhere, what do I mean by the dot? Even though I know all of you know what this is, but just to have our notes complete, this is what I mean by the dot over here. So what we are doing is, we are taking this vector field, we are using the tangent vector of gamma, we are taking their dot product. This is now a function. This is now a function on C. So then I can use the previous definition to define this integration, okay? And before I take questions on this important definition that we are going to heavily use, let me mention some other notation for star. So you will encounter a lot of different notations for this definition star. And there are reasons for it. Some of them are simply that conventionally something else was used. But let me make the first remark. So other notation. So you may see the following notation. So if F is written as F1 to Fn, then you will sometimes see the notation F1 dx1 plus all the way up to Fn dxn. And people might write gamma or they might write C. Doesn't it's the same thing. This is the same thing as F dot ds. Okay. And this is in the language of differential forms, which I do not want to go into right now. But this is just treat this as a formal object. That's what it is. And so this notation sort of you will encounter. Is there a question?
No, I think someone by mistake would have.
Okay. So I can go up to 7, no? So Shobhan, or do I have to stop early? Like.
No, you can go up to 7. Yeah.
Yeah, sorry, I wasn't sure. Okay, great. So this is one notation, and maybe later on, if we have time, I can bring out a little bit more of what the purpose of this notation is. But there's a second one that I want to mention here. So suppose gamma is regular. Then what I do is I set capital T of small t as gamma prime t divided by the norm of gamma prime t, which is the unit tangent field on gamma. And so what will happen is that if you now look at the right hand side over here, so if you look at the right hand side up here, what I can do is I can secretly multiply and divide by the norm of gamma prime t. So here I'll have to multiply by gamma prime t because gamma prime t is the non-zero vector. So then what happens is that all of this simply becomes, so what I had defined as f dot ds on C is actually technically f dot t. This is now a scalar, and I'm simply doing scalar integration. So sometimes you'll also see this notation, f dot t ds. And just to emphasize, because again, it's important that you recognize these things when you see them in the above situation. So which is that gamma is regular, or rather, let me make this comment a little differently. Oh, actually, so maybe I'll skip this comment for the moment. It's not necessary. Maybe it will save some time. And I will only verbally say what I want to say so that we can at least state one theorem for the day. So let's look at these two definitions, and then I'll pause for questions as well. So the first definition is independent of reparametrization, whether you have orientation reversing or orientation preserving. Okay, so the orientation doesn't play a role when you're doing this this particular scalar integration. Okay, it has no effect on this. So for example, computing the arc length of a curve, it would be an example like this. However, when you integrate vector fields along curves, let me say that orientation preserving reparametrizations preserve the integral, while orientation reversing change the sign. So that's why we have to become extra careful when we are doing integration of vector fields along curves. Okay, so before we sort of head towards, so I mean, in every lecture, I sort of want to do one theorem. So before we head towards that, let me see if there are any questions at this stage about these two definitions over here.
Madam, is there any logic behind the definition? That means why we are assuming this type of definition?
For the vector integration.
For this star.
For the star, right. So it's sort of the logic that I was saying about what's it called, the circulation. So you kind of want to see how well, so at least in physical terms, what is happening is that you have your vector field, it's pointing in some direction, and you have your tangent vector, which is pointing in some direction. And a sort of a natural way to get a quantity out of this is to take the inner product. It sort of tells you how much f is in the direction of t, right? Sort of the inner product measures that. So if f was completely perpendicular, you would get a 0. So that's one of the reasons. So if you're trying to understand how much of f is being captured along the curve, so this vector field, it's going in some direction of its own. But how much of it is going along the curve, that ultimately should contribute to the integral. So the way you capture how one vector goes along another vector is by taking the inner product. So that is the idea. It's like if somebody asks you, so if this was a line, okay, so for the moment, if this curve was a line and somebody gave you this particular vector f, and somebody asked you how much of f is along this line, then you would take an inner product, right? You would take an inner product in the direction of this t over here. Does that make sense?
Yes, ma'am. Then in this way, if we forget about this c, if we take the integration over some region, so it will represent the surface like the tangent and normals like the same thing, because the same type of definition is there in R2 maybe.
Yeah. So in R2 also, we will sort of do the same thing, right? We will take the, okay, so in R2, so see, one thing is that we have to be a little bit careful. In R2, we sort of, these two also have to have some, yeah, it is sort of the same thing. But in R2, we do it against the normal. And when we do it against the normal, that does not pick up the circulation, it picks up the flux. So it does represent a different physical quantity, okay? So when we come to surfaces, I will revisit this point. But you may be thinking that, okay, here we often do f dot t. And then if I have a surface in R3, for example, then you might see me doing something like f dot n over there. And n is the normal over there. So of course, first of all, remember that when I take the dot product of f with something, both of them have to be a 3-dimensional vector. So one of the reasons is that these two are compatible. So we will integrate things like this also along the surface. And there you will more be interested in how much of capital F is in the normal direction to the surface. But the logic is the same. Now, if you want to do capital F along the surface, if you want to see its tangential behavior, then you have to be careful because at any point you have two linearly independent tangent vectors. So there, this becomes a more complicated issue. So how do I take one vector field and understand what its tangential behavior is? So that is why more often we try to understand what its normal behavior is. But physically, this gives you a different quantity. This gives you what I was calling flux earlier, and what I was explaining over here gives you more like circulation. But it's exactly the same idea. Whenever you take dot product with something like P or N, you are looking at the component of the vector field in that direction. So you're picking up how much of the vector field is in that direction.
Thank you, ma'am.
Okay. All right, let me just keep track of time. Okay. So let us quickly motivate it's actually not going to take us that much time to prove. Next time, I'll sort of make sure that we come to the theorem a little quicker. But this theorem is a little bit motivated by the following question, which again has physical significance. So given a vector field F on Rn, so let me write it as, in mathematical notation, and assume whatever level of regularity you want to assume. When does there exist a C1 function capital Phi on Rn? It could be a region also. I could be doing this on a specific region U, but for now, let's just do Rn. So when do I have a scalar function such that when I look at the gradient of Phi, and what is this? So this is del Phi by del x1. So this itself is giving you a vector field. Then this gradient spits out exactly this vector field. So if somebody gives you a vector field, how do you know that it's coming out of a gradient? So in this case, Phi is called a potential, not the, because they could be multiple, or you should think about whether they could be multiple, is called a potential of F. And this is not just a mathematical exercise. Potentials are important objects. So for example, if you have come across the phrase Newtonian potential, it is exactly this object where capital F is the force field exerted by gravitational force. So in physics, often when you see the word potential, it is truly the potential of some force field in this context, exactly in this context. So, so the question is, when can we identify whether capital F is coming from a gradient or not? And the first theorem, which a lot of people don't even really refer to as a fundamental theorem, but I will call it one. So gradient theorem. This gives you a necessary condition. So at least capital F has to satisfy this for it to be the gradient of a potential function. So let U be an open connected region in Rn, P from U to R be a C1 smooth function. Then for any Z comma W in U and any piecewise C1 smooth curve gamma from some closed interval into this set capital U, such that gamma of A is Z and gamma of B is W. So what am I doing? Let me draw this picture. I have some connected region. It could have a hole if you want. I have 2 points, Z and W, and I'm taking a piecewise regular curve that connects Z to W. And I have some sort of a function defined on this entire U. Then for any such curve, if I look at the gradient of phi, which is a vector field, and I do its integration along this curve gamma, then all that matters. Okay, so my screen is behaving funny. All that matters are the values of this. I'm sorry, so my screen is giving me some trouble. Okay, let's see. Okay, just give me half a second so that this stabilizes. Okay, I think this is there. Okay. So it's saying that when you want to, so this is like your fundamental theorem of calculus, but I'm saying this for the gradient of a function. And what we are saying is that it doesn't matter what this curve is. I could be doing this for another gamma like this. But at the end of the day, if you're integrating a gradient function, so a vector field that is coming out of a gradient, then all that matters is the value of the function at those two endpoints, okay? And rather than prove this, so I mean, the proof is actually straightforward and maybe it doesn't really matter, you can look this up, but the point is somewhere, let me make this point a little bit more clearly. So if you have some sort of a force field, then what does this represent? It actually represents the work done to move a particle from Z to W in this force field. So it could happen if that you have to work against this force field to move a particle, and the amount of work you need to do is captured by this integral. And if your capital F is the gradient of a potential function, then this work only depends on the 2 points. It doesn't depend on what path you take to do that work. That is kind of the crux of this theorem. Okay, so I think this is not, since it's almost time, it's not a bad place to stop. We will be looking at sort of surface and region versions of this next time. Next time I'll sort of focus on Green's theorem, a few applications, and so on and so forth. So you want a reference. Yeah, sure. So I looked at a couple of, so you can look at Apostol's multivariable calculus. And there's also a nice book by William Wade, which is, I think, called Introduction to Analysis. And these are also so good sources for problems. Some of the problems in your tutorials might also be from these two books. Yeah, let me stop here. Let me see if there are any other questions or any clarifications I can make before I log off about anything that we discussed today.
Ma'am.
Please go ahead.
Ma'am, I have a doubt related to the definitions of A to E, which in the beginning.
The very beginning.
About yes. So one of the definitions, regularity.
Mm-hmm.
In the first part, before that example of square, I could see physically all the things which you were discussing, like all the terminologies were visible.
Okay.
At least on paper, like we could draw them. How can we draw? How can we see by on picture at least or on a paper that a function is regular? I want to know.
Good. So that is the reason why I raised these questions. That whether so we have to separate the curve from the function. Now the point is that whenever you don't have these corners, you will always. So when I say corners, what that means is that locally, and this should remind you of one of the theorems you probably have done this week. If I take any point locally, can I view that piece of the curve as a graph of a smooth function over the tangent space over there? So if you look at my star or asteroid over here, first of all, if I look at just these circled areas, then it doesn't look like I can look at that corner as some sort of a graph of a smooth function. It is a graph, yes, but there is a problem over here. So anytime you have this, you will never have a regular parametrization, okay? So this is one thing that I now want you guys to think about a little bit more. So this is one way to detect it. But if I look at a smooth area, like the circle, then it will have a regular parametrization, but it does not prevent it from having irregular parametrizations, because remember that gamma prime t can also become 0 if you stop at the same place for some time. So that is my answer for the first question. So I take the same parametrization, but let's say I stop at a place for some interval. I don't move. So my curve is moving. Then I stop here for some time. Then I start moving. So I'm still tracing out the circle, but for some time, gamma prime is going to be 0. So the point is, if you desire a regular parametrization, then your curve has to have no corners of these kind in the way I described. That means there exists a regular parametrization, but that doesn't mean that if somebody has given you a parametrization, it will be regular. Because it could be happening that the person is just stopping for some time. But as soon as there is a corner, you just cannot have a regular parametrization. That is the distinction I'm trying to make. So it is a hard question, but in one direction it's easy, right? If you see a corner, if you see locally that you cannot write it as a graph of a smooth curve, then you know there is no regular parametrization. Does that help?
Yes, thank you, ma'am. Thank you.
This about irregular parameterization of circle, could we just take like something like cos 2t, I mean cos t square sine t square?
You mean the square is inside?
Yeah.
Okay.
So when we differentiate, we get a 2t outside, which makes it 0 at 0.
At 0. Good. Okay, sorry, bad differentiation. This is terrible differentiation. But so hang on, but you'll get this. So you're getting sine of minus sine of t squared 2t, right? That's what you're doing. And then you're doing cos of t squared. Yeah. So you're sort of at the very beginning itself, you're sort of adding issue.
Yeah.
Excellent. So this answers this question. And yeah, and sort of the geometric thing to think about is that irregularity also happens not just because of corners, but because of you just kill the velocity of the particle over there. And this should also make you think about the square. So that's a good answer, and it should make you think about the square. Suppose I want a C1 parametrization, but it's okay if it's irregular. Then what I can do is I can start moving towards the corner in a way that the velocity becomes 0 over here. And then I can try to start increasing my speed. So what will happen is that you will get a C1 parametrization, but gamma prime t here will be 0. So you kind of slow down at the corner so that you can move in a C1 fashion, and then you pick up speed again. So here's a way to think about this first question for the square. This question for the square. Sort of similar idea. Okay, have I gone way over time? Okay, but it's okay. If there are questions, it's better to answer them right now. All right.
Just another question. So when you said corners, it's still easy to visualize corners in if it's in R2. I mean, do we have a mathematical definition of corner, or it is just it? I mean, it is just way to see it. I mean, just visualizing it.
It's basically what I said right now. What I said earlier is that if you have something even in space, you kind of locally want to be able to represent it as a graph. So what will happen is if you have a curve, like how do you get a curve in R3 as a graph? So it has to be a graph over, it has to be like, okay, how can I say this? It's sort of the same idea, I suppose. But maybe I'm thinking about how. Yeah, at the end of the day, you basically want to be able to write it like this locally. So t comma gamma t comma sigma t. So let's say we are in R3. Then, yeah, so this is what I mean by a graph. So how do you locally try to identify this curve over here? You should locally be able to view this as some sort of t comma gamma t comma sigma t, where these two are now smooth, gamma and sigma. I know this is still an analytic answer, unfortunately, but this is the rigorous answer.
Okay. Okay.
Locally, you can apply this. So that I'm going to give the keywords away. Implicit function theorem. Okay, so that's the point. So you can locally view it like this. But I mean, visually, it has to be what we said.
Okay, thank you.
Thanks for the question.
Okay, so I think should we stop then? Yeah. Okay.
All right.
Yeah.
All right.
Thank you, Purvi, and we will meet again tomorrow. Yeah.
I'll log out from both devices.
Yeah, sure. Okay, so we will take a break and we will meet at 7:10 for the tutorial. Yeah, I'm just saying the participants. Yeah. Okay, so I will also create a break. I'll create two breakout rooms, and you could choose the same breakout rooms which was assigned previously.